Okay, class. Yes, now the last chapter of modern physics is left, nuclei. So in the last class, we completed with atoms, and this is nuclei is also a very small lesson. This will not take so much of time. See, the basics of nuclei involve understanding the concept and the meaning of some terms. So nucleons are the first terms that are involved. Protons and neutrons are collectively called as nucleons. Protons plus neutrons, these are together known as nucleons. Now, atomic number is also there. Atomic number means number of protons. So this is represented by Z. Understand the symbols because now we'll be using the symbols only. Then you have number of protons plus neutrons, which means number of nucleons. So both the number of protons plus neutrons gives mass number. So mass number is represented by A. Fine. Atomic number as Z, mass number as A. Now class, number of protons plus neutrons is A. So number of neutrons will be A minus Z. So again, I'm repeating, number of protons will be Z, number of electrons will also be Z, and number of nucleons will be A, from which number of neutrons become A minus Z. Now, how to represent an atom? You just write the chemical symbol like helium, so you'll write He, calcium you will write Ca, argon you will write Ar, right? Chlorine you will write Cl, sodium you will write Na, whatever is the chemical symbol of it. And the topmost corner you will write the mass number, and on the lower left corner you will write the atomic number. Fine. Now 4 quantities are there: isotopes, isobars. Let's discuss it. Usually these are not asked in your exams, these terms, but let us still discuss if by chance it comes. See, isotopes mean you have same Z, that is same atomic number, but different values of mass number. Like hydrogen. Hydrogen has 3 isotopes: protium, deuterium, tritium, right? One has C on the lower sides, that is all the mass. You have the atomic number same as 1, but mass numbers are different. Protium has 1, deuterium has 2, tritium has 3, like this. So these are known as isotopes. Many elements have their isotopes. In chemistry, you all must have studied about isotopes. Then you have isobars. In isobars, you have same mass number, but you have different atomic number. Like chlorine and sulfur, if you talk, then both are having the mass number almost 37. If you take the 37 value of chlorine, that is 37, and sulfur is 37, but they are having different atomic number. Sulfur lies prior to in the periodic table than chlorine. Similar is an example of calcium and argon. Both are having 40 as the same mass number, but different atomic number. Calcium comes last. Argon is in the 18th group, right? So these are the differences between isobars and isotopes. Same Z, different A, same A, different Z. But 2 more quantities you have over here, which are isotones and isomers. So isomers we are not going to do. Isomers you have it in chemistry in detail. But isotones just analyze. They have A minus Z same. That is same number of neutrons. So like chlorine has 37 and 17. Potassium has 39 and 19 as mass number and atomic number respectively. But when you take the difference here also for chlorine, you're getting 20. For potassium, you're getting 20. So such numbers where A minus Z results in the same variation. Those are known as isotones. Fine. So these again, I'm repeating the basic terms. Isomers you have, which are the same chemical representations, or you can say different structures. Isotopes, same atomic number, same mass number, same atomic number, different mass number, and isobars, same mass number, different atomic numbers. And for isotones, you have same number of neutrons. Note down these points. No, that is mass number. See, atomic number, the proton number is Z, which is written here. Written.
Yes, ma'am.
Okay. Now see. So these were the basic terms. Usually questions are not asked from this. See, some atomic masses you have to remember because usually they are given in the paper, but many questions I have seen where the masses of electron, proton, neutron are not mentioned in AMU, atomic mass unit. So it's better at least three values you have to remember. Minimum three values are there. So at least you can remember these three. See, hydrogen, you can directly add neutron and proton. So that you can do during the paper only. But otherwise, apart from that, you all should remember the values. So mass of electron is 0.00055 AMU. Mass of proton is 1.0073. Mass of neutron is 1.0086. And the mass of hydrogen is complete mass of proton plus complete mass of neutron. Fine. 1.078, it won't be this much. If you add 1.0073 and 1.0086, it will be greater. Right, 1.0159 you will get 1.0159 around it. But at least mass of electron, mass of proton, mass of neutron class, try to remember these values. Fine. Do one thing. Okay, let's discuss this only, then you can note it together. C class, this is also important, which is the nucleus size. So nucleus size says volume of a nucleus is directly proportional to its mass number. Volume of a nucleus will be 4 by 3 pi r cube and mass number is A. So 4 by 3 pi r cube, if you look from here, r cube is directly proportional to A. So from here, if you remove the cube or take the root, you will get r is proportional to A to the power 1 by 3. Here you put a constant r naught whose value is 1.2 Fermi meter fixed. Class, if it is mentioned in some questions, you will see r naught's value is given to you. 1.3 Fermi meter, 1.1 Fermi meter. Like this, the values can be given. If it is not given, you will straight away use this value 1.2 Fermi meter. Now, I hope you all know what is Fermi. Fermi is just like nanometer, picometer, angstrom. You use the conversions for length. Similarly, Fermi meter means 1 Fermi means 10 to the power minus 15 meter. Remember this, 1 Fermi 1 Fermi meter. Here this is equal to 10 to the power minus 15 meter. So remember this for conversion. Anyways, so R is the radius of the nucleus, A is the mass number. Usually you get the values where the cube roots can be calculated, but even if you do not get, you have to solve it till the last step. And questions are very easy from nuclei. For you people, nucleus is very easy. Now, class, if we calculate the nuclear density, density will be mass of nucleus divided by volume of nucleus. See, when you write mass of nucleus, mass, let's say small m is the average mass of a nucleon. Average mass, because so many nuclei are there, we cannot calculate for a single one. So let's say it is R naught is just a constant. Like you can write K, we can write any constant. So it's written as R naught. It's a constant because when we remove the proportionality sign, we have to put in a constant. Usually it is written as K, so we consider it as constant. Here it is R naught, so do not get confused. R naught means constant only. Through experiments, it has been calculated that this is around 1.2 Fermi meters. Now class, you will then multiply it with the atomic mass. So mass by volume, 4 by 3 pi r cube. So put the value of R as R naught cube by A, R naught cube into A. See here class, R is equal to R naught A to the power 1 by 3. So R cube will be R naught cube A. So same thing here, 4 by 3 pi r cube. So put this value instead of r cube. You'll notice mass number is getting cancelled. 3m by 4 pi r naught cube is left. And when you put in the values of this class, this is asked a lot in your exam. When you put the value, you get the value as 2.3 into 10 to the power 17 kg per meter cube. It is independent of mass number means. For helium, you will write 2.3 into 10 to the power 17 kg per meter cube. For boron, you will write 2.3 into 10 to the power 17 kg per meter cube. Same with aluminium, same with lead, same with calcium, same with sodium, same with potassium. This value remains independent of the mass number. Whatever is the mass number given, you will write the density, which will remain constant. All right, for all the elements, because you can notice A got cancelled in your answer, whereas A was present in the radius. Radii depends. Radius is directly proportional to the mass number, but the density is independent. And these two topics are very important, and most probably questions will be from these two topics only, because rest of the portions have been deleted from the syllabus. So these are very important. Do mark it as important. Let us practice some questions on this also. Note it down first, class. Written till here. See, it says that calculate radius of germanium whose mass number is given as 70. And see here, like in this question, R naught is mentioned as 1.1 Fermi meter. So here when R naught is mentioned, you will not use 1.2 Fermi meter in this case. You will use R naught as 1.1 only. So see, radius is R naught, a to the power 1 by 3. So R naught is 1.1 Fermi meters, a is 70. 71 by 3. So 4 cube is 64. No, so this will be around 4. Around 4 something. Let me check this. So 4.12. This will be around 4.12. So 1.1 multiplied by 4.12. So 1.1 multiplied by 4.12, this will be around 4 only, 4.5, 4.5. So this will give you 4.532 Fermi meter. Because I have not converted Fermi here, so answer will come in Fermi meter. And then express 16 milligram mass into equivalent energy. This is from your last lesson only. E is equal to mc square. But questions will be from nuclei. It means the weightage will be from this lesson. 70 cube root of 70 by long division method. And sometimes you can approximate it also. Like 4's cube, you know, it's 64. So more than a little more than 4 it should come. So you can use 4 and you will get the answer approximately same. 4.1 you can use 4.12 like this. Otherwise, if you want to get precise answer, properly use long division method and calculate it. Now mass is 16 milligrams, so 16 into 10 to the power minus 3 kgs. This is the mass. Mass I have converted into kg into speed of light whole square. Fine. So that makes 9 into 16. That is 144, right? 144 into. So that makes it 16. Then we have minus 3 also. No? So that will be 13. So 10 to the power 13 joules. Note these two questions, then we'll see some more questions. See, this says that assuming protons and neutrons have equal masses, you have to calculate how many times nuclear matter is denser than water. So basically, you have to compare the density of the nucleus and density of water. So density of nucleus is the same density of nucleus 2.3 into 10 to the power 17 kg. So this will also be 2.3 into 10 to the power 17 kg per meter cube. And when you have to write the density of water, that is, yes, what is the density of water? Density of water. In SI unit, what is the density of water? Yes, yes. Fahad, you have just written kg per meter. I'm not asking SI unit. I'm asking the value for water. Madhya, correct? I will write it as approximate to 1000 kg per meter cube. Now we have to compare this. Yes, 997. 997, just write it at 1000. 1000 will work. 1000 kg per meter cube is enough. Now take the ratios, ratio of nuclei by water. So 2.3 into 10 to the power 17 by 10 to the power 3. So that will be 2.3 into 10 to the power 14. 14 ratio will get, the units will get cancelled. So this much denser it is. 2.3 into 10 to the power 14 times is it denser. Now last question. C class. In the last question, it is saying the nuclear mass of iron is 55.85. Calculate its nuclear density. C class, even if you change it for iron and these data whole stories will be given, ultimately you have to find out nuclear density. Nuclear density, no matter what you put it as, iron you put it as, sodium you put it as, any element, nuclear density will always remain 2.3 into 10 to the power 17 kg per meter cube. So if such questions are asked for 3 marks or 2 marks, then you cannot obviously write just one line and leave it that density is 2.3. You'll have to show the working. Just now, no, you have written it above where you had shown how you got 2.3 into 10 to the power 17. That part you will show. The density is mass by volume, putting everything, and it is independent of mass number and how you're getting that part if it is asked. If it is for 1 marker, then you just have to mention the value. Note down this as well, class. Then we'll do some theory portion from here. 1000 is the density, no? So density 1000 can be written as 10 to the power 3. So that same 1000 is written as 10 to the power 3. See class, this is another topic from this lesson from which questions can come, mass defect. So mass defect is what? See how to write this and how to memorize this entire formula. Mass of a single proton is mp and number of protons that are available are z, atomic number. So total mass of every proton, it will become zmp. Mass of single proton is mp. Total number of protons are z. So total mass of protons will be zmp. Similarly, mass of a single neutron is mn and mass of the entire neutron is a minus z. In the beginning only we had seen these terms z, a minus z and all. So total mass of neutrons will be a minus z into mn. And total mass of nucleus, we are assuming that this is mn. Now what is mass defect? Mass defect is total mass of protons plus neutrons first. So that's why Zmp plus A minus Zmn, mass of protons plus mass of neutrons, minus the mass of the nucleus. So minus Mn. This is known as mass defect. Like this, if you remember the formula, this entire formula you will be able to remember. Mass of single proton MP, total number of protons Z, so total mass will be ZMP. Mass of a single neutron Mn, total number of neutrons A minus Z, and then the total mass of neutrons will be A minus Z into Mn. And total mass of nucleus is Mn. So when you add both the masses and subtract mass of nucleus, you get mass effect. Now a term is known as binding energy. Binding energy means suppose there is a nucleus and due to presence of some external forces, you have separated all the components of nucleus, protons, neutrons, you have successfully separated it. So the energy that is now generated or emitted when once the protons and neutrons have released from the nucleus, this is known as binding energy. All right. Now binding energy is actually equal to mc square, but here m is your delta m. Delta m is the mass effect. So delta m into c square. C, you know, speed of light, 3 into 10 to the power 8. Meter per second. So this is speed of light. So binding energy is delta mc square. Delta m is the mass, change in the mass. C square is the speed of light. So ZMP plus A minus ZMN minus Mn, this is mass effect multiplied by C square. Now binding energy per nucleon means binding energy per unit, per mass unit. Means if you divide the binding energy by mass number, then you get binding energy per nucleon. So binding energy per nucleon means ZMP plus A minus ZMN minus Mn into C square, that is the binding energy divided by A. Whatever the answer you are getting for binding energy divided by the mass number, you get binding energy per nucleon. But go step by step. First find out delta M, that is mass effect. Then multiplied by C square to get binding energy. So complete binding energy will be delta M C square. Now class, writing every time c square, that is 3 into 10 to the power 18, is difficult because many a times you will have to write your answers in electron volt. So we better write, you get mass effect, but multiply it by 931 mega electron volt. Whatever answer you will get, that answer will be in mega electron volt and that will be considered as well. So binding energy is delta M into 931 mega electron volt. Fine. So instead, just get mass effect properly by following all the above mentioned steps. But when you are reaching your final step, instead of multiplying it by c square and then dividing it by 1.6 into 10 to the power 19 and then converting it, it's better you multiply it by 931 mega electron volt. Otherwise, if needed, you will multiply it by c square only. Both are valid. Both are accepted. All the values of what? For these, it will be given. See, Z, A minus Z, I mean, these will be given. But many a times, mass of proton and mass of neutrons will not be given. So that I have made you write earlier only atomic masses. And mass of nucleus will be given. And mass number, yes, details, other details will be given. Which details can be missing, that I have told you. Before doing this question, I think note down this part. Then we'll practice this numerical from here. Then you are almost towards the end of this lesson. This is a very short lesson because radioactivity has been deleted from your syllabus. So do not revise radioactivity for your boards. Yes, class. Now see, this says that calculate the binding energy per nucleon of calcium. 40-20 nucleus, given mass of neutron, mass of proton, mass of calcium. Like here, mass of neutron and mass of protons are also mentioned. And mass of nucleus is given. Calculate, class, try it by yourself. Then after 5 minutes, I'll discuss it. See, do not round it off here. In this case, no, here in binding energy question and in the entire questions of nuclei, do not round it off. Fine. If it is 1.0086665, take it as it is. Do not round it off here. And then see what answer you're getting. See, calculations are not very difficult. Addition, subtractions will be involved. At least tell me delta M first. Mass of nucleus is this only, mass of calcium atom. This is the mass of nucleus. Mass of calcium's nucleus is given. Okay, let me discuss it now. So delta M will be C Z MP, right? Plus A minus Z Mn minus mass of calcium. So ZMP, no. See here, Z is 20. From this, you can figure it out that Z is 20. So ZMP will be 20 multiplied by 1.00782 right? No, 1.00782. This multiplied by 20 will give 20.1565. Now, mass of neutron, A minus Z. So A minus Z is also 20. A minus Z is also 20. So A minus Z Mn. That will be 20 into 1.00, then 8665. This multiplied by 20 will give 20.17. This should give 20.17. No, just check. 20.173. 20.1733. So total neutrons plus protons will be, see, 20.1733 is here. Then you will add 20.1565. So that will be around 40. Total, this will be ZMP plus A minus Z Mn will be, sum of these, that will be 40.3298. And now you have to subtract the mass of nucleus, that is calcium. What is it given? 39.962589. Right. So 39.962. 39.962589. 589. So when you'll subtract these, you'll get it 0.367211. Class, do not round it off here. So this is mass defect. You have to calculate binding energy per nucleon. So binding energy will be, or per nucleon will be divided by A. This will be 0.367211. This will be multiplied by 911. Right. See class, directly this conversion, 931, this conversion directly, which I have told you, this will give you your answer in direct mega electron volt only. So now I do not have to perform any conversions. Binding energy 341.87. Yes, right. Binding energy is this much. So this multiplied by 931 divided by the mass number. Mass number is given as 40. So see, this will be, Fahad rightly answered, 3.41873 divided by 40. This should be around, when it is divided by 40, it will be around 8.54 something. How much Priyadarshini was getting? 8.546. Perfect. Correct answer, Priya. This much mega electron volt per kg. All right. Noted down, class. Any doubts you have, please ask me. See, last topic is binding energy curve. This binding energy curve is properly given in the notes that I've shared on WhatsApp. So no need to copy this curve. This basically shows you the binding energy, whatever you have studied about binding energy, but the experimental results. These were just the calculation parts, no, that we have done it by ourselves. The experimental parts, binding energy and if mass number both are plotted. Right. So on one axis, y-axis, we have binding energy and on x-axis, we have mass number. It was observed that the binding energy for initial few elements, it increased. For the binding energy, it kept on increasing along with the mass number. As the mass number increased, it kept on increasing. Like for hydrogen, helium, certain elements, it also increased. Fine. But then it was observed that for hydrogen, as soon as helium is reached, then there was a dip observed for lithium. Then again it rised for carbon. Then again it fell for nitrogen. Then again it rose for oxygen. And one more dip was here that I have not drawn in here properly. That is present in your notes. So initially you see hydrogen, all the three, these HH which I have written on, these are actually the isotopes of hydrogen, protium, deuterium, tritium. So all these are in one line. They are increasing as the binding energy is increasing. Mass number is also increasing till here, but then it is decreasing as the mass number increase. See, mass number is still increasing. Mass number is constantly increasing, but variation is observed for binding energy. Binding energy decreases for nitrogen. It decreases for lithium. One more element was there. I think boron is also here, where one dip is observed for boron also. Then again, it was observed after oxygen, it again started increasing. And then one point was reached for iron, after which it didn't increase. It increased till iron. And see here also it should not be 50, it should be 56. Here you should get 50 and here you should get some other value so that you can get in between here, you can get the value as 56. So 56, because you know the mass number for iron is 56. In chemistry, you all have studied this. So some concept of chemistry you have to apply when you are studying this. Right. So iron is 8.8 mega electron volt. This was the value of highest value of binding energy that was observed for the elements that are present in your periodic table. But then after iron, all the elements that are having mass number more than 56, you all must be remembering some elements that have mass number more than 56. Some have 107 also, like silver and all, some elements. I do not remember the mass numbers right now, but the other mass numbers, you must be remembering it. So after 56, it then, as the mass number was increasing, binding energy kept on decreasing, as you can see also here. Here is the value around 7, then here is around 6, here around 4 point something, here around like this. It kept on decreasing. This is not a very proper graph to copy. In your notes you will see a very clean graph is given, and even in your NCERT. So binding energy curve, this actually relates with your nuclear fission and fusion. And since your nuclear and fission and fusion are not a part of your syllabus, so chances are there that this graph may not be asked. So two topics that we have completed in this lesson, this mass defect part, this mass defect part can be asked. And please remember these formulas. It looks like this question won't come because this is having such huge long values. No class, this question can be asked to you, right? And then the first topic which we did was the nuclear size and nuclear density. These two topics are also very important from this lesson, nuclear, right? So that finishes off with your nucleus, and this also completes with the unit modern physics. Now one last chapter is left, that is semiconductors. Semiconductors, we'll try to complete it on Thursday. It's longer than atoms and nuclei. Nuclei and atoms both were very short lessons. No, nuclei was even smaller than atoms. Just two topics are present in nuclei, which we discussed. So in your semiconductors, even these topics have a little detail because theory part is also asked. Go through the notes that I have sent you on WhatsApp. Any doubts you have? How many classes? One class. It should, maximum portion will be completed in the next class only. 2 hours class is enough. Some, I think one more hour, if half an hour or more will be needed, I think that we'll be able to analyze on Thursday only. Fine. Otherwise, most probably it should end by the next class. Not a very huge lesson. I have told you in the beginning only, ray optics takes huge time. After ray optics, every lesson covers so much less time. Fine, so you all can leave now. You all can leave. Any doubts you have, you can ask me. And class, try to have your weekends free, because most probably your revision classes will be on weekend only. Timing and rest of the things, once